right, you're good.
All right. So we're going to talk about moisture first and some of the consequences of it. I would love to talk about how I caught this fish. I actually caught it by hand, okay, in the ocean. So we'll come back to that if we have any time. Just to show you, I have a keen interest in water activity. I used to have a boat that was called Water Activity 2. This was my second one. And we used to have undergraduate parties out there all the time, but we sank it. So that didn't do much good for it. So why is water content important? You've taken already the food chemistry class, and you know about it in terms of microorganisms and texture, chemical reactions. It's also a special thing in commerce. For example, in grains, there is certain requirements that you can't be above a certain water content, because that would be economically cheating. You can be lower, but you can't be above that. So for example, for wheat grain, it's 40% moisture at 50% relative humidity. Fish meal, it's 12% moisture. These are set by government standards. The one for fish meal is actually set by the U.S. Coast Guard, because we ship a lot of fish meal on barges around the country, usually coming from plants down in Louisiana. And fish meal above 12% moisture is very, very explosive. It can catch fire because the fats in it are so highly unsaturated that reaction will catch it on fire in there. So, so you learned already about microgrowth, chemical stability, texture like Christmas versus rubbery, soft cookies, and stickiness. So we're going to look at this from the standpoint of moisture sorption isotherms. If we plot moisture content versus water activity, we get a curve that looks like this. Usually we plot moisture on this side and water activity there, but this allows us to cover a wide range of things. There's a certain water activity that above that moisture content, there's a large change in moisture for a very small change in water activity. If we do adsorption versus desorption, you're going to see a very interesting thing. We call it hysteresis, that there's two different moisture contents at different water activities. Two different water, this is moisture contents at a given water activity. That's breaking thermodynamic law. But the reason it's different is that there's changes in the material itself that change the ability for picking up moisture. And so it's not really violating any thermodynamics. But that's important to know, because if you're drying something, you want to really know the desorption curve, versus if you're putting potato chips in a package, you're going to be on the absorption curve. And this just points out some of the foods. For example, grapes, 95% water, 19 grams of water per gram of solids on a dry basis, and a water activity about 9.7. This is beef jerky here, just below about 50% moisture. That's 1 gram of water per gram of solids. That's where this starts flattening out. Gummies, about water activity of 0.7, about 20% water on a wet basis, and 0.25 grams of water per gram of solids on a dry basis. Then we have a mixed product, which has raisins and cereal in it. So you've got 2 water activities and 2 moistures for it. And down here we have the crispy products like potato chips, which are about 3% water, or 0.031 grams of water per gram of solids. So this just shows you some products that fit on these curves. And what we want to know is, why are we doing all of this? Well, it's from the standpoint of water activity. So we need to have a moisture versus water activity curve in there. And once we have that, we can then use these paradigms. For example, you know, if we're somewhere in this range, we call it a monolayer range, that a dry food has the longest shelf life. It's very, very stable. If you go higher, a crispy product is going to lose crispness. A sugary powder, such as milk powder, it can get sticky. On the other hand, if it was a raisin at a 0.65 water activity on that previous graph, when it gets down to 0.55, the raisins get too hard. So another problem that we have. We generally, when we're out in the plant, we generally don't use water activity as a control mechanism. We use moisture content because it's easier to do it that way in there. But we have to have that relationship between both the moisture content and the water activity. 0.7, 0.8 is the maximum in chemical rates, and then 0.85 is the onset of bacterial pathogen growth. A number of you doing capstone are going to be doing water activities on your product because it's going to be important from the standpoint of shelf life. So here's something we'll be talking about in more detail. How do we make a moisture sorption isotherm? What we have is desiccators with saturated salt solutions in them, in the bottom, and those salt solutions produce a given water activity or relative humidity inside that chamber. For example, sodium chloride slurry, it's got to be a slurry. Sodium chloride slurry at room temperature is about 0.76 water activity. So we report moisture different ways. Wet basis, so grams of water per 100 grams of total food. So that includes the water and the solids in it. And we can convert that to percentage by multiplying by 100. We also have dry basis, which is the percent water over the percent water wet basis in here times 100, and that's grams of water per 100 grams of dry solids. And then solids non-fat. In the dairy industry, they always talk about solids non-fat. If you add fat to a food, the moisture content is not going to change, but on a total basis, the water is really reacting with all the other materials, the starches, the proteins, all the other molecules in there. And so people like to look at it as grams of water per gram of non-solid, non-fat solids. You've done the statistical part with Pam?
Yes.
Talking about
Yes,
it?
we've done.
So I'm just going to skip over this
Yes.
because
They know.
I know you have it. Just to point out precision, if we look at this set of data here, and we plotted it, let's say, as a target. This one up here, there it is. It's too small. This is high accuracy, but low precision. This is low accuracy, but high precision. So that's one way you can look at when you're talking about accuracy versus precision. People get that thing always mixed up in there. For moisture contents, in most cases, the precision is about 2% to 5% of the moisture percentage. So if we had 5% moisture, the precision is about 0.25%, telling you how precise you can be between measurements. So, how do we get rid of the water so we can measure water content? Simplest thing is to put it in the chamber, have heat in the bottom, which passes up through here, heats the product. We maybe put 40, 50 samples in here, and we wait for a given amount of time. So what we have that's been done for us is that you can go to two standards, the American Association, the Association of Official Analytical Chemists, AOAC. In fact, they're having a meeting sometime next semester in Minneapolis in there, and we're doing some work with them there. And then American Association of Serial Chemists, which now is, they changed it, International Association?
Well, but Chelsea has a different
It's
name.
AACCI. So American Association.
AACCI, yeah,
Did
international.
you say that it wasn't American anymore? Or no, that was something else?
So you're thinking of AOAC?
Yeah.
Official or American?
No, or AOC.
AOA, Association of Official Analytical Chemists.
It's community, or was it?
Communities now, not chemists, because there's more than just.
Is that right?
Yeah, that's changed.
I didn't know that.
Mhm.
I didn't either, Ted.
Okay. So you can do that heating of your product at different temperatures. So you want to know how long should you do it to do that. And if you go to these books that they have, you look up meat, it'll give you a very specific time and temperature for meat. If you want it faster, it'll give you data on how long you should hold it at different temperatures so that you're going to get the same number at the lower temperature for a different amount of time in there. So this has all been done very, very well. Their precision is, for this oven, is about 2% of the measured moisture content. One of the problems is opening and closing this. There's time for temperature recovery. And very importantly, the pans at the bottom shelf are going to get more heat than the pans above. And so what you'd be best to do is ignore the 3 levels and only put samples in the middle tray in there. But that increases the amount of work you've got to do because you have to have another thing or just longer time in there. So that's one of the real problems we have with an oven like this. We'll talk about some other problems in it. If we want to heat it, do it faster and not damage the product, because you put something like a raisin at 100 degrees C in one of these ovens, you're not going to have a raisin anymore. You're going to have, it's going to have a lot of chemical reactions, and the Maillard reaction produces water. So you would get more weight loss because of the Maillard reaction. So in a vacuum oven, you have less resistance to mass transfer, so it's better, and less thermal degradation because the water boils off or vaporizes off at lower temperature. Typically 26 to 28 inches of vacuum, 18 to 20 hours at 65 for meats and flesh foods, and about 5 hours for cereal grains and cereal products in there. Very importantly, the water is coming out, it's going to a vacuum pump. What you want to have before the vacuum pump is a cooling chamber where you condense out the water into the trap. We call it a trap. Why would we do that? Yeah?
Vacuum pumps don't like water.
Yeah, it don't. The water gets, those cheap vacuum pumps are vanes, and they get water on them and they're going to get rusty. Okay, and then eventually you're not going to have a vacuum in there anymore. It's not going to work, so that's not very good. So you need that. The vacuum, however, does increase volatile loss because there's more escaping tendency. And again, you can have the poor temperature distribution. Usually these are smaller, so you only have 2 trays in here. And since there's no air, convection is not as important in there. It's more radiant heating that's doing it. But you definitely need that trap in there. Out on a plant, you want something, you don't want to wait for 18 to 24 or 48 hours. So you want something that's fast. And so 60 years ago, there were new devices that came out that basically had an infrared lamp. You close this over, your sample was put in a pan, and then you push the button here to heat it turn the lamp on so it would radiate to the food, and it would heat the food and lose the water vapor in there. When we first started working with these were ugly instruments. Unfortunately, I threw all my old instruments out just recently. But this one's very modern. You know you got a problem when you open it up and the sample is burning. Not a good thing to have. And again, there are some standards that are used for this. Generally, you're talking about 4-minute measurement of moisture in there. And as long as you got the right conditions, and what you want to do is standardize the time here to some other laboratory in your laboratory method so that you know that you're getting the same moisture content in it. And that's part of the work of setting up a quality control system in a plant. Generally, it's 400 degrees Fahrenheit, so it's rapid. It's good for quality control, quality assurance, but it's not AOAC approved. Okay, so that's a critical thing there. So you definitely have to standardize it. And I've just listed here 5 different companies. There's probably 30 companies out there selling these instruments. And they've all changed from, in the old days, they were pan balances, and you had to put weights to match the weight on it, and now it's all digital stuff, so it's a lot easier to use. This is the Sartorius one. It says, determine the moisture content with a few minutes, accurately and reproducibly. That's bullshit. You have to set up some standards yourself.
Did you just say BS?
I said BS, yes. Come on, it's a real word.
It's recording.
Huh? Am I going to go to jail?
Maybe.
Yeah.
Don't they come with programs?
Huh?
Do they come with programs for different foods, like?
Some of them have programs, yes. Yeah, but you basically, you know, if you're going to do a granola bar, it's not going to be in the book anywhere. So you have to set up your own standards. You know, that's the real problem. Yeah, if it was whey powder, there's some standards that the dairy industry has set for it on that. This is another rapid method, 1 sample at a time in a microwave oven. You weigh your sample onto a pad that goes in the middle here, and then they have some standard set up, and then again, they're going to be doing this too, right? The microwave?
Yes, they
Yeah,
will.
in there. Which other ones?
What's that?
Which other methods? The oven method?
The convection oven and the
Vacuum oven.
And then Karl Fischer.
And then Karl Fischer, okay. One can also freeze dry. So you take your sample, you put it in a vacuum oven, but this vacuum oven is operating at about 0.1 millimeters of mercury. So the vacuum pump for that is a very special pump, and they run about $15,000 to $20,000. Definitely you want to trap on something like that because you don't want to replace it. The problem with this is 48 to 75 hours. You know, so it's not worthwhile for doing moisture contents. What it's worthwhile for is making a dry sample, if that you want minimal chemical reactions taking place in it. So we do a lot of stuff like that, making up samples and then doing that. You can also do it very simple with not much equipment. You can have a desiccator with dryerite calcium sulfate in it. It's approximately at 0.1 millimeter mercury. It's about 0.5% relative humidity. If you have something dry in there and you put in your wet food at a higher water activity, higher moisture content, you know, the water is going to go into the dryerite over time. But it's slow. It's very slow. In general, it's around 2 weeks, but it could be up to 3 weeks. So it's not a quality control method at all. But it is a way of producing a very dry sample if you want it for research purposes. You can also use sulfuric acid solution. In the old days, when I was an undergrad, we did use sulfuric acid in there. And the worst problems, we had glass desiccators, and you couldn't get the top off the desiccator. And so you'd wear a rubber coat and eyeglasses, stuff like that, you know, when you're careful trying to take the cover off in that. And the other is phosphorus pentoxide. It produces 0.005. If you got organic volatiles in the food, they're going to be absorbed also by the phosphorus pentoxide. And I had a very interesting experience. I was on a quarter leave in Australia, and I got a call in the middle of the night from the safety officer for the university here. One of my students wanted to get very dry glycerol and propylene glycol, so she put them in the desiccator with phosphorus pentoxide inside, and it just happened that one day while I was gone, and she was gone to try to get some information from confectionery companies. She was in England, and the guy came by, looked in the hood. It was in the hood, okay? But he saw this thing bubbling in there. And there was, she unfortunately didn't put any information on it, so they found out it was my lab. They called me, and I said, yeah, that's my lab. They said, you know, you've got phosphorus pentoxide now bubbling, and that it's very explosive in there. So they called the bomb squad, the university, and took it somewhere, and they dropped something on it, and the thing all blew up in there. See what you can do in the laboratory.
Fun.
So here's problems. Sometimes you want to do liquids. You want to do a moisture content on a liquid. And what's going to happen is the liquid is going to spatter in there. And so what you do generally, and this would be also for fats. Let's say you want to take an oil and see what the water content is. There's some water in it. And so you add sand in there, a weighted amount of sand, to have it in that sample itself. And that sort of prevents that from happening, which is useful. You can get losses of moisture if you're going to grind your food up. We usually do that because we want a homogeneous sample on it. We can get weighing losses in there. If we have large non-homogeneous samples like granola bar, what do you know, the different parts in that bar in the beginning are going to be very different in water activity. And so the moisture content is sort of not meaningful to that. And that's a real problem for the industry. And the question is how long does it take to equilibrate so that all the water activities are the same? And it's going to depend on the bar geometry and what else is in it, so that's a very difficult thing. Sugars can collapse and flow and trap water in it, and then when they recrystallize, you may, like with lactose, you'll get water of hydration, which has a very, very high enthalpy to remove that water from it. So you have water in the system, but it's trapped as a hydrate of the lactose, but it could get released later in any process. So that's a critical issue that we have as well. So here are other problems. Decomposition during drying. Drying time is proportional to, in this case, because we have it in cups, it's proportional to the thickness or the height, the depth of the sample, squared. So if I had a sample that I poured in that was twice as high as the sample next to it, that was the first level that you used, it's going to take 2 squared, it's because it's twice as deep, 2 squared, so 4 times longer to heat, to dry. That says you got to have a uniform sample in there for your duplicates. Yeah?
Is that true in the vacuum too?
Yeah, well, yeah, it is true in a vacuum, yeah. Because that's just standard unaccomplished moisture equations. There's a log function that does it. If you have volatiles like glycerol and propylene glycol, they are going to be lost as well. And so it's not a very good way to try to measure moisture when you have that. And typically those are used in semi-moist confectionaries and semi-moist bars, stuff like that. Propylene glycol, we have found out that it was a cause of killing many cats, specifically cats, and so the FDA, after 20 years of, the data was found, it was the work done here in the vet med school, and we still use it in food. I avoid any food with propylene glycol. I mean, I don't think, if it's killing a cat, it's gonna take just longer to kill me. If you dry too hot, with vegetables especially, what you do get is the heat takes that pore that's losing water, and that pore now goes over its glass transition and it collapses. And so you get something called case hardening. And so you trap the moisture inside the product, and then that's not, you're going to get a false reading for if you use the standard time. So it's especially a problem with dehydrated vegetables. You want to cool before weighing, because you're going to, if you put a hot sample on your balance, you're going to get convection currents, and it's never going to go to a level, you know, where you can read the weight of it. So you should cool it in a desiccator, especially if you've got a humid environment, which in the summertime, it's pretty humid around here. At least 50 to 60% relative humidity indoors. And so that's a critical thing. And again, these are the same equations that I showed before, so I'll skip them. So that's the simple ways that people measure, except for Karl Fischer. We'll talk about Karl Fischer in a few moments. One typical thing that was done in the 50s and 60s, and I'm not sure anybody does it anymore, but you put your sample in here, and you add toluene to the sample, and then you heat it up to distill it, and you get an azeotropic formation. So the toluene and the water go up, and they go into this portion. That's a condenser, and so it falls down into a tube here, which is actually graduated in milliliters, tenths of a milliliter on there. The water is heavier than toluene, so the water falls to the bottom, and you heat it for a certain amount of time, and then that tells you how many cc's of water came out of the sample. Typically done with spices. I don't know why spice industry picked that all the time. Unfortunately, toluene is a carcinogen, and here we're heating it, you know, and some of it is coming out of the condenser. Not all of it is going to be trapped, and so we stopped using that. People went to xylene, but then they found that was a carcinogen, and now they're using trichloroethylene. The only difference here is that it's more dense than water, so the toluene goes down to the bottom, and the water stays here, and you got more toluene in the sample, so you got to have a new tube that's much longer in there. Otherwise, you can't see all the water in the thing. Simple method, about half an hour of distilling, and then you just read the tube in there. That's why people liked it, because it was a rapid method. Another thing you could do is you could mix your food, ground up food, with methanol, and then filter it so you don't have no particles, and then take the solution sample and inject it into a GC. And there are 3 or 4 companies, PortaPack is one of them, PortaPack Q. They make a column that will have a peak for water. And so you can do it today with automated GCs. So that's a very simple method. The question is, how long do you need to mix it with the methanol? And in general, we have found with dehydrated type of foods, not with wet foods. It's not going to work very well with wet foods. But for dehydrated foods, it's about 18 hours. So an overnight on a slow shaker is enough to get the extraction of the water into the methanol. And then you just measure the height of the peak, and you can make a standard curve for that. So how about solvation with a chemical reaction? Again, the same thing. You extract with dry methanol. Methanol is highly hygroscopic, so you have to keep it in a very closed container, and you should always measure the water content of the methanol as well. So a blank in there. So the typical Karl Fischer method, use sulfur dioxide reacting with pyridine and iodine, and that takes one water, and this produces these compounds slowly here, that in there. And what you did was you did this reaction, ground up sample in with the in this solution. The solvent that you use was pyridine. And pyridine, we didn't know when we were doing this in the early days that it was a carcinogen, but people could smell that you were doing it 2 blocks away. Okay? That says there's something wrong going on in there. So it was basically a titration system that what would you use to detect iodine? Starch, yeah. So the starch will react with the iodine and turns blue. And so you keep on titrating until you think you're done, and then you measure the optical density and you make a standard curve from that. Then we started getting automated titrating systems that you would just put the solutions in there and it would do the titration for you. But always you had, it's very hard to get a cell that's not going to leak. And so you can get up to, we did a lot of work on that, about 20 microliters of water per minute from outside if you had a 50% relative humidity. So that's not very good. The stoichiometry of this limits the amount of water. So when you're doing this kind of titration, you can only do it in a certain limit. So what you do is if you have a very wet food, you use a smaller sample. If you have a dry food, you use a larger sample. And in some of the Karl Fischer books, like this one here, which you want back there, it gives you some information on how to do that in there. Now, the Karl Fischer you have gets rid of most of this because it uses a coulometric method to produce the iodine. And it just produces enough iodine to react at the same level with the amount of water that's in the system. So it's a very simple electronic system that does this. Doesn't use pyridine, so you don't have any problems with that. And it prints out, or on LEDs, you read the amount of water in the system. In terms of, is it microliters on that one, or is it micrograms? I think it's microliters, yeah.
Yeah.
So, for example, on these coulometric ones, like the one that we use, you have a range from 10 micrograms of water up to 200 milligrams of water. So you'd adjust your sample weight to be somewhere in that range so that you could get it. And the resolution is very good, about 0.1 micrograms. There's a lot of industry has gone over to this as an internal standard. You get rid of all the other problems that we heard about. It's fast, except for the leaving it overnight to get the extraction. You do a sample also with the blank methanol, so you subtract that because you're going to put a certain amount of methanol into your sample cell, and so it's a fairly good method. I'll send to Cindy a paper that we wrote for IUFOST on looking at different methods of moisture content. It'd be worthwhile reading, and you could distribute it to the class. Recently, I think it was about 3 years ago, some companies came up with another method, is that you put it in the cell, react it, and you then suck out a sample and it goes through a GC column to give you a reading of the water content. I am not sure how good that works. I've not, a friend of mine in Germany is the world's expert. He's a co-author on the paper. He's an expert on Karl Fischer, and he feels that it's never been proven to work very well in there. So here's that system. That's the automated one. where here's the cells and here's the starch solution, and it does that, and that's all hooked up to a computer here that then gives you the answer. And this is similar to the cell that you're going to be using. That's just the coulometric system. So 0.1 to 0.15% moisture wet basis is the precision here. Now, here's the problems with Karl Fischer. Yeah?
What is the colorimetric?
There's a grid in there, okay? And that grid senses the water, okay? And as the water is being produced with the iodine, it's iodine is being injected, and there's a solution that has the iodine in it. And so one molecule of water is used up, for one molecule of iodine that's reacting, so it just causes the titration by measuring the current in that grid, or the amperage in that grid. It's pretty it's a pretty fast system to do that. But here's our problems. You don't know. Yeah, question.
So for the titrator, how do you judge the color change?
How do you judge it? The color change, you go take a sample out and measure the optical density. So you got to make a standard curve, okay? Because it gets darker and darker and darker as it's producing it. So extraction can be incomplete. We spent a lot of time working on this. My first research grants were from the military, Department of Defense, and basically we were working on shelf-stable, freeze-dried foods for the astronauts. And so they wanted some good quality control methods, so we looked at these things in water activity and stuff like that, and came up with these. Bubbles in the syringe, you use a syringe to extract 100 microliters. Is that the one that you're using, 100 microliter syringe? Or 10 microliter?
Is it a syringe?
Yeah,
10 or 100.
I think it's 100, right?
Yeah.
Yeah, so what we do is we extract, we go and weigh the syringe, then we go and squeeze it and push it into the cell to react, and weigh the syringe again, and so that will tell you how much methanol that the solution you've injected into the cell itself. So that's basically there's two steps. You extract the sample, you got it in a shaking, small Erlenmeyer fast. You now open it, take a sample out of it, and you inject it into the Karl Fischer device and push a button, and it goes, and in a few minutes or so, it'll tell you how much water is in the sample. So pretty easy system to work with. As I said before, the methanol absorbs water, so you need a blank. Solids in solution can corrode the grid, and they usually last about a year or so, and they're about $300, $400 to replace in there. You can tell that because it starts getting corroded, and you don't want to use that anymore because that's going to change the resistance. And then the other thing, if you got high-fat food, the methanol is going to dissolve some fat as well. And if it's unsaturated, under those conditions, you can get very fast reaction of the iodine across the double bond, so you get the iodine being used up by the fat, not because of the reaction with water. So that's a problem in there. Here's my favorite one, the Alpha Lux Speedy Moisture Meter, a company in England, and it's used for measuring moisture content of cement. Why would you want to do that?
Determine the strength of the cement when it cures?
Well, to not determine the strength, but for a given outside temperature, if you pour cement, there's a very specific amount of moisture that you don't want to go above in there, otherwise it'll never set. especially when they're trying to pour cement during the winter time. In Minnesota, at some point, you don't do that anymore, you know, in there. So that's what is, it's also used for rats. Why rats? Well, you're not nutrition majors, huh? You know, if you do animal studies, at the end of a 2-week feeding trial or whatever, you measure the weight of the animal. You also want to know the water content of the animal. So you take the fat, the rat, you euthanize it. You then freeze it in liquid nitrogen, and then grind it up in a grinder. And then you take a sample of this.
Cindy says no.
No? They don't do it? That's how I did it.
I think they just don't do this kind of research much.
Yeah, I know. That's.
When
Yeah.
they take a sample, yeah.
Yeah.
Continue this.
Yeah. You have a metal container that's got a pressure gauge on it, okay? So you unscrew the gauge, you throw your sample in there, and
The
then
rat, you mean?
yeah, the rat sample. You add calcium, what's it, calcium carbide? I forget, yeah, I think calcium carbide in there. What happens is the calcium carbide reacts with the water to produce acetylene. So it produces a gas, and it raises the it raises the pressure, and so the meter, instead of measured in pressure, it tells you how many grams of water is in the sample in there. So very good. The soil people use it a lot too. And here's just an example of what one looks like. This is a very small one. This is a little bit larger. You can see it here using there. That's at a cement factory using it. And it's, you know, I mean, how precise it is, I don't know. I try to get information from the company, but they still sell it to, for rats. They got tables on rats and stuff. Now, the last thing, we got what, 5 more minutes?
Yep, 6 minutes.
6 minutes. Yeah. Is I would like to have a system that I can put on a line, and I did a lot of work with ocean spray on the craisins. So you got craisins coming out of a drying oven, and they had their pile 6 inches deep, and they wanted an automated system. And first thing I says, let's go to 2 inches deep, because you're never going to get a good measurement on that. So what you can have is use a device that's an NMR, and just measure the T1 relaxation from that instrument, and you can make that as a model that would shine onto the row of the conveyor belt, and so it would give you an immediate reading as a thing. You would need to calibrate it for each food. It's good between about 5 to 25% moisture if you're using NMR methods in there. And there's some methods for doing it. This is a typical type of device. I did a lot of work with 3M when they decided to get rid of organic adhesives and use water instead. So they had to recalibrate everything. And there you got, you know, a thin film, so it gives you a very good thing. With a pile of food coming out, it doesn't work very well. And I also did it with one of the world's largest cookie makers in Belgium. They had an interesting system. They had it was about a 200-yard long oven tunnel. So the cookie doughs would be deposited on trays going into that, passing through the oven. And there were gas stages along the oven so that you can control the heat. And then they had 3 guys at the end. One was looking at the color, one was picking one up and tasting it, and the other one was there ready to pull a chain. So if it was getting too dark, he'd pull a chain and you'd hear beep, 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 beep. That meant there was 10 people who ran to the oven, and the too dark color says turn the gas valve 1/4 away this way. That was their quality control system. Now it's completely automated with with, instead of this is the near infrared way of doing it. You can buy these instruments, near infrared, and they say it can measure moisture content, fat content, and protein content. Well, you just can't take a odd sample and put it in there and get numbers that are good. You have to have a standard for each of these in there. It uses different wavelengths for water content, for protein, and for carbohydrate. It's a good quality control tool once you have precision on comparing it to other methods. So you've got to do that in there. It uses these water bands, 1 minute per sample. It's a good QA/QC tool, but you need that calibration. Neotech is probably one of the better ones. There's a fat, moisture, and protein simultaneously, but it's not a research tool. You can't take a product off the shelf somewhere and then put it in there and get a number that's going to mean anything in there. And then the last one is these kinds of devices here. You have a tube. You see that metal thing sticking up inside? That's an electrical connection. It's isolated from the wall. You put your sample up here, grain. You push a lever, the grain drops down into here. So you have a certain volume, it drops down into here. And then it measures the conductance across that tube in the middle with the outside wall. So it's basically measuring an electrical property to it. So you need to have a standard curve for each kind of grain. And this is used by all the grain inspectors. They go out and this is how they check the moisture content of grain to see whether you're in that 14% or lower region in there. Very, very simple. The old one I had was not working very well. This is basically dielectric constant is the critical part of this. This is an automated one. It's got, these guys used to carry books around and they find out first the variety of the grain, then look up the pages for that variety, and then look down columns, tables, and they would get the moisture there. Now it's all electronic in a small handheld device. And here's all these readings and stuff. There's a very small one that does it. And that one a silver medal in 1996. And then lastly, for solutions, you can use hydrometers. These are glass tubes sealed, usually with lead particles in the bottom, but nowadays we don't want lead in the plant. Okay, so they use other metals in there. And it has a percent water or percent alcohol or percent salt or percent sugar on it. So it's for this was actually designed for the beer industry back in, where's the date? Oh, I thought there was a date on here. But it was in the 1800s they did this to ensure that for beer and this has come back now with all these these craft beers, that people have different percentages of alcohol, so they use it for that. I'll stop here. The last thing is refractometer, and I'll just touch on it at the beginning of the next class.
Thank you. Have a great weekend. Happy studying. Okay, good.